This is Team 23105 at University of Arizona's College of Engineering Senior Design Project. Wildfires in the United States are natural disasters that resulted in approximately 3,800 civilian deaths just in the year 2021. In the same year, there were around 59,000 wildfires, which affected more than 7 million acres of land. Our senior design project was to use sailplanes or gliders for terrestrial uses, and our team chose to deploy our system to combat wildfires, which have prominently affected the United States, especially California and Arizona. This project is aimed to act as the first step in wildfire aid, response, and rescue, and this video will explain our challenges, discoveries, and endeavors over the last 1 year of working on this project. Our project is titled SAIL, which stands for Support Aerial Incendiary Locator. Our team consists of 5 engineers who led various different operations to make SAIL a success. Maximus Chen, our controls and team lead, Caitlin Hackworth, our aerodynamics lead, Manya Kapoor, our systems lead, Yashvardhan Singh, our powers and communications lead, and Alton Zhang, our structures lead. The concept of operations proposed for our final flight start with a takeoff mechanism, which utilizes the use of a weather balloon to gain a desired altitude. This takeoff stage approximately takes an hour to climb to the altitude before finally releasing our glider system to map its path over a specific region of interest. In our case, a wildfire-struck landmass. It glides over the region, constantly relaying necessary information in the form of location data, as well as thermal and regular imagery, which is our first tool towards aiding in wildfire detection and appropriate response. What you see on your screen is a clip from our onboard thermal camera, which detects ground-based heat signatures for a number of different settings.
We wanted to analytically verify whether or not our prototype would work. Thus, we created a model of it inside of XFR5. By creating a model of the parachute itself, plus the paraglider body nacelle, we were able to determine aerodynamic coefficients such as the coefficient of lift and the coefficient of drag. Utilizing these aerodynamic coefficients, we were able to understand just how our body reacted during flight, and we were able to go ahead and calculate important things such as optimal speed, sync rate, and we utilize those for our autopilot.
We began our flight testing regime by setting out to collect flight data from our prototype. We equipped the SAIL paraglider with integrated memory storage so that the instrumentation data being fed to the flight computer would be recorded on board. As you can see, this information was collected and extracted to contribute to our analysis of the flight characteristics. It also allowed us to refine the autopilot parameters in preparation for turning over control of our paraglider to the flight computer in the autopilot. Before we could do that, however, we needed to prepare the telemetry systems that allow us to receive live data from the paraglider in flight. The footage you can see now is from our second test flight, where with only a laptop and a small radio antenna module, we are able to communicate with SAIL in flight to give it commands while receiving information in real time to provide to the pilot. Finally, we had collected enough data that we are confident SAIL could fly on its own. On our latest test flight, we nervously watched as our prototype sailed into the air and prepared to switch into autonomous flight mode. To our relief, the modified program performed beautifully, allowing the paraglider to loiter high above without any human intervention. Our current prototype is hand-launched, and this will remain an option for operators who don't need to fly at high altitudes for a more rapid deployment of the system. Once in the air, the pilot can step back and allow the ground operator to maintain control. Using open-source mission planner software, the operator can direct the autopilot and monitor the flight through GPS and instrumentation data. Once over the area of interest, the thermal camera system can then be engaged. Now that you've seen our system in action, I'll walk you through its components. The camera payload is made up of a thermal camera, the FLIR Lepton, that links to a pure thermal processing board and an Odroid computer. These components convert the image into a format that can be transmitted through the telemetry system. The same dual telemetry system is also used for communicating with the flight system. The flight system is made up of a flight computer that runs the autopilot, a GPS, an airspeed sensor, and all the motors on board, along with a power distribution board and a battery.
This is the original body that came with the paraglider kit. The original body is not a very aerodynamic shape as it is only intended for low-altitude recreational flights. Our next step was to design the nacelle to replace the paraglider body we purchased, since nacelles are a much more aerodynamic shape. Since our project focuses on easy and affordable manufacturing and assembly, the nacelle is designed around existing components from that body. The replacement nacelle has the servo arms mounted internally to reduce drag, but has slots on the lid to still allow for the required servo arm authority. The motor mounted to the original body has been fitted to the new nacelle with the option to remove it when powered flight is not needed. There's a small hole at the front of the body for the pitot tube, and a hole on the bottom of the nacelle for the thermal camera to observe below. All of our previously tested electronic systems are included inside of the nacelle as well. The last system needed to achieve the goal of Project Sail is the parachute deployment and release system. Since the paraglider will be dropped from a high altitude rather than climbing on its own, a method to deploy the parachute right before the balloon pops needed to be developed. First, the parachute was dropped from a short height to observe how the wing would open when released. This informed us that the wing best deployed when folded in a tri-fold configuration. After this, a method to suspend and release the parachute in this configuration was developed. This was achieved by sewing loops and key rings onto the center of the wing and each wingtip. These rings and loops are then held by a cabinet lock which releases when a signal is received. This signal will be sent by the autopilot using the inbuilt relay function. Now that we have tested the release mechanism on the ground and performed a feasibility analysis, the final step towards the completion of Project Sail is to deploy the paraglider on the high-altitude balloon flight. During this flight, we will confirm that all of our systems are integrated and function as desired, as well as collect more in-flight data. This will allow us to make any necessary modifications to our final prototype.